Inductively coupled plasma mass spectrometry is a type of mass spectrometry which is capable of detecting metals and several nonmetals at concentrations as low as 1 part in 1012. This is achieved by ionizing the sample with inductively coupled plasma and then using a mass spectrometer to separate and quantify those ions. Compared to atomic absorption techniques, ICP-MS has greater speed, precision, and sensitivity. However, analysis by ICP-MS is also more susceptible to trace contaminants from glassware and reagents. In addition, the presence of some ions can interfere with the detection of other ions. The variety of applications exceeds that of inductively coupled plasma atomic emission spectroscopy and includes isotopic speciation. Due to possible applications in nuclear technologies, ICP-MS hardware is a subject for special exporting regulations. Components: inductively coupled plasma. An inductively coupled plasma is a plasma that is energized by inductively heating the gas with an electromagnetic coil, and contains a sufficient concentration of ions and electrons to make the gas electrically conductive. Even a partially ionized gas in which as little as 1% of the particles are ionized can have the characteristics of a plasma. The plasmas used in spectrochemical analysis are essentially electrically neutral, with each positive charge on an ion balanced by a free electron. In these plasmas the positive ions are almost all singly charged and there are few negative ions, so there are nearly equal amounts of ions and electrons in each unit volume of plasma. An inductively coupled plasma for spectrometry is sustained in a torch that consists of 3 concentric tubes, usually made of quartz. The end of this torch is placed inside an induction coil supplied with a radio frequency electric current. A flow of argon gas is introduced between the 2 outermost tubes of the torch and an electric spark is applied for a short time to introduce free electrons into the gas stream. These electrons interact with the radio frequency magnetic field of the induction coil and are accelerated first in one direction, then the other, as the field changes at high frequency. The accelerated electrons collide with argon atoms, and sometimes a collision causes an argon atom to part with one of its electrons. The released electron is in turn accelerated by the rapidly changing magnetic field. The process continues until the rate of release of new electrons in collisions is balanced by the rate of recombination of electrons with argon ions. This produces a Fireball unregistered trademark that consists mostly of argon atoms with a rather small fraction of free electrons and argon ions. The temperature of the plasma is very high, of the order of 10,000 K. The ICP can be retained in the quartz torch because the flow of gas between the 2 outermost tubes keeps the plasma away from the walls of the torch. A second flow of argon is usually introduced between the central tube and the intermediate tube to keep the plasma away from the end of the central tube. A third flow of gas is introduced into the central tube of the torch. This gas flow passes through the center of the plasma, where it forms a channel that is cooler than the surrounding plasma but still much hotter than a chemical flame. Samples to be analyzed are introduced into this central channel, usually as a mist of liquid formed by passing the liquid sample into a nebulizer. As a droplet of nebulized sample enters the central channel of the ICP, it evaporates and any solids that were dissolved in the liquid vaporize and then break down into atoms. At the temperatures prevailing in the plasma, a significant proportion of the atoms of many chemical elements are ionized, each atom losing its most loosely bound electron to form a singly charged ion. Mass spectrometry. For coupling to mass spectrometry, the ions from the plasma are extracted through a series of cones into a mass spectrometer, usually a quadrupole. The ions are separated on the basis of their mass-to-charge ratio and a detector receives an ion signal proportional to the concentration. The concentration of a sample can be determined through calibration with certified reference material such as single or multi-element reference standards. ICP-MS also lends itself to quantitative determinations through isotope dilution, a single-point method based on an isotopically enriched standard. Other mass analyzers coupled to ICP systems include double-focusing magnetic electrostatic sector systems with both single and multiple collector, as well as time-of-flight systems. Applications: One of the largest volume uses for ICP-MS is in the medical and forensic field, specifically, toxicology. A physician may order a metal assay for a number of reasons, such as suspicion of heavy metal poisoning, metabolic concerns, and even hepatological issues. Depending on the specific parameters unique to each patient's diagnostic plan, samples collected for analysis can range from whole blood, urine, plasma, serum, to even packed red blood cells. Another primary use for this instrument lies in the environmental field. Such applications include water testing for municipalities or private individuals all the way to soil, water and other material analysis for industrial purposes. In recent years, industrial and biological monitoring has presented another major need for metal analysis via ICP-MS. Individuals working in plants where exposure to metals is likely and unavoidable, such as a battery factory, are required by their employer to have their blood or urine analyzed for metal toxicity on a regular basis. This monitoring has become a mandatory practice implemented by OSHA, in an effort to protect workers from their work environment and ensure proper rotation of work duties. Regardless of the sample type, blood, water, etc., it is important that it be free of clots or other particulate matter, as even the smallest clot can disrupt sample flow and block or clog the sample tips within the spray chamber. Very high concentrations of salts, for example sodium chloride in seawater, can eventually lead to blockages as some of the ions reunite after leaving the torch and build up around the orifice of the skimmer cone. This can be avoided by diluting samples whenever high salt concentrations are suspected, though at a cost to detection limits. This technique is also widely used in the field of radiometric dating, in which it is used to analyze relative abundance of different isotopes. ICP-MS is more suitable for this application than the previously used thermal ionization mass spectrometry, as species with high ionization energy such as osmium and tungsten can be easily ionized. In the field of flow cytometry, a new technique uses ICP-MS to replace the traditional fluorochromes. Briefly, instead of labeling antibodies with fluorochromes, each antibody is labeled with a distinct combinations of lanthanides. When the sample of interest is analyzed by ICP-MS in a specialized flow cytometer, each antibody can be identified and quantitated by virtue of a distinct ICP footprint. In theory, hundreds of different biological probes can thus be analyzed in an individual cell, at a rate of circa 1,000 cells per second. Because elements are easily distinguished in ICP-MS, the problem of compensation in multiplex flow cytometry is effectively eliminated. Metal speciation, a growing trend in the world of elemental analysis, has revolved around the speciation of certain metals such as chromium and arsenic. One of the primary techniques to achieve this is to use an ICP-MS in combination with high-performance liquid chromatography or field flow fractionation. There are many advantages, from a clinical standpoint, in knowing the specific species present within a patient's body. For example, one species of chromium, known as trivalent chromium, is needed by the body and causes no ill effects. However, hexavalent chromium is very toxic to the body. Chromium-6 can cause mutations that may lead to cancer if not repaired by the body. http pubs/axorgabsac 00110A023. It is also beneficial for a clinician to utilize speciation analysis from a preventative standpoint. Many patients, who suffer from elevated levels of certain metals, do not know when or where the exposure incidents are occurring. By identifying the exact species, a physician can better narrow the search for possible exposure sites, therefore helping the patient to avoid certain areas in the future. Quantification of proteins and biomolecules. There is an increasing trend of using ICP-MS as a tool in speciation analysis, which normally involves a front-end chromatograph separation and an elemental selective detector, such as AAS and ICP-MS. For example, ICP-MS may be combined with size exclusion chromatography and quantitative preparative native continuous polyacrylamide gel electrophoresis for identifying and quantifying native metal cofactor-containing proteins in biofluids. Also, the phosphorylation status of proteins can be analyzed. Recently a new type of protein tagging reagents called metal-coded affinity tags were introduced to label proteins quantitatively with metals, especially lanthanides. The MiCat labeling allows relative and absolute quantification of all kind of proteins or other biomolecules like peptides. MiCat comprises a site-specific biomolecule tagging group with at least a strong chelate group which binds metals. The MiCat label proteins can be accurately quantified by ICP-MS down to low atmol amount of analyte, which is at least 2-3 orders of magnitude more sensitive than other mass spectrometry-based quantification methods. By introducing several MiCat labels to a biomolecule and further optimization of LC-ICP-MS detection limits in the zeptamol range are within the realm of possibility. By using different lanthanides, MiCat multiplexing can be used for pharmacokinetics of proteins and peptides or the analysis of the differential expression of proteins, for example in biological fluids. Breakable page SDS page, two-dimensional gel electrophoresis or chromatography is used for separation of MiCat labeled proteins. Flow injection ICP-MS analysis of protein bands or spots from DPAGE-SDS page gels can be easily performed by dissolving the DPAGE gel after electrophoresis in staining of the gel. MiCat label proteins are identified and relatively quantified on peptide level by MALDI-MS or ESI-MS. Elemental analysis. The ICP-MS allows determination of elements with atomic mass ranges 7 to 250. This encompasses lead to U. Some masses are prohibited, such as 40, due to the abundance of argon in the sample. Other blocked regions may include mass 80, and mass 56, the latter of which greatly hinders Fe analysis unless the instrumentation is fitted with a reaction chamber. A typical ICP-MS will be able to detect in the region of nanograms per liter to 10 or 100 milligrams per liter, or around 8 orders of magnitude of concentration units. ICP-MS is a method of choice for the determination of cadmium in biological samples. Unlike atomic absorption spectroscopy, which can only measure a single element at a time, ICP-MS has the capability to scan for all elements simultaneously. This allows rapid sample processing. A simultaneous ICP-MS that can record the entire analytical spectrum from lithium to uranium in every analysis won the Silver Award at the 2010 PyTCon Editors Awards. Hardware. In terms of input and output, ICP-MS instrument consumes prepared sample material and translates it into mass spectral data. Actual analytical procedure takes some time. After that time, the instrument can be switched to work on the next sample. Series of such sample measurements requires the instrument to have plasma ignited. Meanwhile, a number of technical parameters has to be stable in order for the results obtained to have feasibly accurate and precise interpretation. Maintaining the plasma requires a constant supply of carrier gas and increased power consumption of the instrument. When these additional running costs are not considered justified, plasma and most of auxiliary systems can be turned off. In such standby mode, only pumps are working to keep proper vacuum in mass spectrometer. The constituents of ICP-MS instrument are designed to allow for reproducible and or stable operation. Sample introduction. The first step in analysis is the introduction of the sample. This has been achieved in ICP-MS through a variety of means. The most common method is the use of analytical nebulizers. Nebulizer converts liquids into an aerosol, and that aerosol can then be swept into the plasma to create the ions. Nebulizers work best with simple liquid samples. However, there have been instances of their use with more complex materials like a slurry. Many varieties of nebulizers have been coupled to ICP-MS, including pneumatic, cross-flow, Bobington, ultrasonic, and desolvating types. The aerosol generated is often treated to limit it to only smallest droplets, commonly by means of a double-pass or cyclonic spray chamber. Use of autosamplers makes this easier and faster. Less commonly, the laser ablation has been used as a means of sample introduction. In this method, a laser is focused on the sample and creates a plume of ablated material which can be swept into the plasma. This is particularly useful for solid samples, though can be difficult to create standards for leading the challenges in quantitative analysis. Other methods of sample introduction are also utilized. Electrothermal vaporization and in-torch vaporization use hot surfaces to vaporize samples for introduction. These can use very small amounts of liquids, solids, or slurries. Other methods like vapor generation are also known. Plasma torch. The plasma used in an ICP-MS is made by partially ionizing argon gas. The energy required for this reaction is obtained by pulsing an electrical current in wires that surround the argon gas. After the sample is injected, the plasma's extreme temperature causes the sample to separate into individual atoms. Next, the plasma ionizes these atoms so that they can be detected by the mass spectrometer. An inductively coupled plasma for spectrometry is sustained in a torch that consists of 3 concentric tubes, usually made of quartz. The end of this torch is placed inside an induction coil supplied with a radio frequency electric current. A flow of argon gas is introduced between the 2 outermost tubes of the torch and an electrical spark is applied for a short time to introduce free electrons into the gas stream. These electrons interact with the radio frequency magnetic field of the induction coil and are accelerated first in one direction, then the other, as the field changes at high frequency. The accelerated electrons collide with argon atoms, and sometimes a collision causes an argon atom to part with one of its electrons. The released electron is in turn accelerated by the rapidly changing magnetic field. The process continues until the rate of release of new electrons in collisions is balanced by the rate of recombination of electrons with argon ions. This produces a fireball, a unregistered trademark that consists mostly of argon atoms with a rather small fraction of free electrons and argon ions. Advantage of argon: making the plasma from argon, instead of other gases, has several advantages. First, argon is abundant and therefore cheaper than other noble gases. Argon also has a higher first ionization potential than all other elements except E, F, and E. Because of this high ionization energy, the reaction is more energetically favorable than the reaction. This ensures that the sample remains ionized so that the mass spectrometer can detect it. Argon can be purchased for use with the ICP-MS in either a refrigerated liquid or a gas form. However, it is important to note that whichever form of argon purchased, it should have a guaranteed purity of 99.9% argon at a minimum. It is important to determine which type of argon will be best suited for the specific situation. Liquid argon is typically cheaper and can be stored in a greater quantity as opposed to the gas form, which is more expensive and takes up more tank space. If the instrument is in an environment where it gets infrequent use, then buying argon in the gas state will be most appropriate as it will be more than enough to suit smaller runtimes and gas in the cylinder will remain stable for longer periods of time, whereas liquid argon will suffer loss to the environment due to venting of the tank when stored over extended time frames. However, if the ICP-MS is to be used routinely and is on and running for 8 or more hours each day for several days a week, then going with liquid argon will be the most suitable. If there are to be multiple ICP-MS instruments running for long periods of time, then it will most likely be beneficial for the laboratory to install a bulk or micro-bulk argon tank which will be maintained by a gas supply company, thus eliminating the need to change out tanks frequently as well as minimizing loss of argon that is left over in each used tank as well as downtime for tank changeover. There are rare ICP-MS solutions that utilize helium for plasma generation. Transfer of ions into vacuum: the carrier gas is sent through the central channel and into the very hot plasma. The sample is then exposed to radio frequency which converts the gas into a plasma. The high temperature of the plasma is sufficient to cause a very large portion of the sample to form ions. This fraction of ionization can approach 100% for some elements, but this is dependent on the ionization potential. A fraction of the formed ions passes through a 1 ohm hole and then a 0.4 ohm hole. The purpose of which is to allow a vacuum that is required by the mass spectrometer. The vacuum is created and maintained by a series of pumps. The first stage is usually based on a roughing pump, most commonly a standard rotary vane pump. This removes most of the gas and typically reaches a pressure of around 133 pascals. Later stages have their vacuum generated by more powerful vacuum systems, most often turbomolecular pumps. Older instruments may have used oil diffusion pumps for high vacuum regions. Ion optics: before mass separation, a beam of positive ions has to be extracted from the plasma and focused into the mass analyzer. It is important to separate the ions from UV photons, energetic neutrals, and from any solid particles that may have been carried into the instrument from the ICP. Traditionally, ICP-MS instruments have used transmitting ion lens arrangements for this purpose. Examples include the Einzel lens, the barrel lens, Agilent's Omega lens, and Perkin-Elmer's shadow stop. Another approach is to use ion guides to guide the ions into mass analyzer along a path away from the trajectory of photons or neutral particles. Yet another approach is variant patented used by Bruker Aurora M90 ICP-MS 90 degrees reflecting parabolic ion mirror optics, which are claimed to provide more efficient ion transport into the mass analyzer, resulting in better sensitivity and reduced background. Bruker ICP-MS Aurora M90 is the most sensitive instrument on the market. Collision reaction cell and CRI. The collision reaction cell is used to remove interfering ions through ion-neutral reactions. Collision reaction cells are known under several trade names. The dynamic reaction cell was introduced by Perkin-Elmer on their Eland ERC instrument and is located before the quadrupole in the ICP-MS device. The chamber has a quadrupole and can be filled up with reaction gases, with one gas type at a time or a mixture of two of them, which reacts with the introduced sample, eliminating some of the interference. The collisional reaction interface technology used in the Bruker ICP-MS is another effective approach to removing interfering ions. It is essentially a mini collision cell installed in front of the parabolic ion mirror optics. The proprietary collisional reaction interface used in the Bruker ICP-MS removes interfering ions. These ions are removed by injecting a collisional gas, or a reactive gas, or a mixture of the two, directly into the plasma as it flows through the skimmer cone and/or the sampler cone. Supplying the reactive collisional gas into the tip of the skimmer cone and/or into the tip of the sampler cone induces extra collisions and reactions that dissociate polyatomic ions in the passing plasma. Fundamentally, CRIs are mini-collision reaction cell destroying ICP-MS interferences using a collisional kinetic energy discrimination phenomenon and chemical reactions with interfering ions similarly to traditionally used larger collision cells. Routine maintenance. As with any piece of instrumentation or equipment, there are many aspects of maintenance that need to be encompassed by daily, weekly and annual procedures. The frequency of maintenance is typically determined by the sample volume and cumulative runtime that the instrument is subjected to. One of the first things that should be carried out before the calibration of the ICP-MS is a sensitivity check and optimization. This ensures that the operator is aware of any possible issues with the instrument and if so, may address them before beginning a calibration. Typical indicators of sensitivity are rhodium levels, cerium oxide ratios and EI water blanks. One of the most frequent forms of routine maintenance is replacing sample and waste tubing on the peristaltic pump, as these tubes can get worn fairly quickly resulting in holes and clogs in the sample line, resulting in skewed results. Other parts that will need regular cleaning and/or replacing are sample tips, nebulizer tips, sample cones, skimmer cones, injector tubes, torches and lenses. It may also be necessary to change the oil in the interface roughing pump as well as the vacuum backing pump, depending on the workload put on the instrument. Sample preparation. For most clinical methods using ICP-MS, there is a relatively simple and quick sample prep process. The main component to the sample is an internal standard, which also serves as the diluent. This internal standard consists primarily of deionized water, with nitric or hydrochloric acid, and indium and/or gallium. Depending on the sample type, usually 5 ml of the internal standard is added to a test tube along with 10 500 microliters of sample. This mixture is then vortexed for several seconds or until mixed well and then loaded onto the auto-sampler tray. For other applications that may involve very viscous samples or samples that have particulate matter, A process known as sample digestion may have to be carried out, before it can be pipetted and analyzed. This adds an extra first step to the above process, and therefore makes the sample prep more lengthy. References. External links.